We've learned a lot in the previous couple of videos. What I think we need is an example that kind of reviews all that stuff with different numbers. In order to make all the numbers work out really nicely, I want to have a polynomial as my function. So my function f of x is equal to 1/3 x cubed minus x squared minus 15x plus 10. And what I want to eventually do is sketch an approximate graph. And I want to emphasize that this is an approximate graph. I don't care so much that the graph looks right. What I care about is that I properly depict the intervals where it's increasing and decreasing and concave up and concave down. As you learned in the previous video, to determine when a function is increasing or decreasing, we need to know its first derivative. So we're going to need to know the derivative of this function. Fortunately, it's a polynomial, so it's pretty easy to figure out the derivative. The derivative of 1/3 x cubed is 1/3 times 3x squared, which is just x squared. And then from that, I want to subtract the derivative of x squared, which is 2x. And from that, I subtract the derivative of 15x, which is just 15. The derivative of the 10, since 10 is a constant, is 0. It doesn't show up in my first derivative. If f of x is 1/3 x cubed minus x squared minus 15x plus 10, f prime of x is x squared minus 2x minus 15. Since I'm not just interested in when the function is increasing and decreasing, but also when it's concave up and concave down, I might as well calculate the second derivative right now. Since the first derivative is a polynomial, the second derivative is going to be equally easy to figure out. The derivative of x squared is just 2x, and the derivative of negative 2x is negative 2. My second derivative is 2x minus 2. The first and second derivatives just kind of talk about how the graph is changing. But I kind of need a starting point. I need somewhere to anchor my graph. And the easiest place to anchor the graph is just at the y-intercept. Because the y-intercept is probably the easiest height to calculate on the graph. Because the y-intercept is just asking, where does the graph cross my y-axis right here? And it's crossing the y-axis when the x value is 0, because the y-axis is right in the middle of the graph. So to figure out the y-intercept, all I got to do is evaluate f of 0, change all the x's into zeros. All these terms go away except for the 10. F of 0 is equal to 10. My graph should go through this point right here that has a height of 10. Now that I know the y-intercept, I can use that as kind of my anchoring point, and I can sketch the rest of the graph based off this. How am I going to do that? First, I need to know the first and second derivatives because I want to locate critical points and inflection points. I've already figured out the first and second derivatives up here, so I can move right on to part 3 where I'm calculating the critical points and the inflection points. For the critical points, I want to know when the first derivative equals 0. Our first derivative is x squared minus 2x minus 15. So figuring out the critical points amounts to figuring out when x squared minus 2x minus 15 equals 0. How would you solve this equation? Well, it'd be really nice if whoever made this problem picked the numbers to make it work out super nice so this would all factor, and I did, and it does. X squared minus 2x minus 15 is the same as x minus 5 times x plus 3. So I got something times something equals 0. Either x minus 5 equals 0 or x plus 3 equals 0. What I'm saying is that solutions to this equation happen when x equals 5 or when x equals negative 3. This graph is going to have two different critical values at 5 and negative 3. What about inflection points? Well, inflection points are kind of similar to critical points, except they're not concerned with when the first derivative equals 0. They're concerned with when the second derivative equals 0. The second derivative we already calculated is just 2x minus 2. And solving for when 2x minus 2 equals 0 is pretty easy. Just add 2 to both sides of the equation and then divide by 2, and we get x equals 1. This graph has an inflection point at x equals 1, and it has critical values at 5 and negative 3. I'm going to add all of those to my graph, even though it'll make things kind of overwhelming. X equals 1 is this point right here. This dotted line does not represent a vertical asymptote. This is just telling me that I have an inflection point at x equals 1. Similarly, at 5 and negative 3, I have critical values, so I'll add those to my graph as well. We're getting close to being at the point where we can sketch an approximate graph. The critical values are going to separate the intervals on which the graph is increasing from the intervals on which the graph is decreasing, and the inflection point is going to separate the intervals on which the graph is concave up from the intervals on which the graph is concave down. But the question is, which side of this is concave up and which side is concave down? Am I increasing over here or am I increasing in here? I don't know those just yet. So far, all I've figured out is when the first derivative equals 0 and when the second derivative is equal to 0, but I don't know the behavior of the first and second derivatives on either points of those intervals. But I have some good news for you. My two critical values has split the graph up into 3 different regions. All the numbers less than negative 3, all the numbers between negative 3 and positive 5, and all the numbers greater than positive 5. And if my graph is increasing at any number less than negative 3, that'll mean that my graph is increasing at all numbers less than -3, because the only spots it can switch from increasing to decreasing are at these critical values. So what I can do is pick any number I want. It doesn't matter which one, any x value that's less than -3. I don't know, -5, for example, maybe. And I'm going to test x equals -5. What do I mean by test x equals -5? I mean put it into my first derivative. F prime of -5 would be -5 squared minus 2 times -5 minus 15. Because remember, my first derivative is x squared minus 2x minus 15. If I figure out what number I get here, -5 squared is positive 25, -2 times -5 is positive 10, and then from that I want to subtract 15. I guess I have 35 minus 15, in other words 20, but really I don't even care about this value. All I care about is that this is greater than 0. The fact that this is greater than 0 means that my graph is increasing at -5. And the fact that my graph is increasing at -5 means that my graph is increasing at all values less than -3. That's really powerful. I can do that same analysis by picking any number that I want in between -3 and +5. I don't know, zeros usually work out really nicely. Let's try testing 0. When I say test, I mean plug it into the first derivative. So I got to evaluate f prime of 0. F prime of 0 is just 0 minus 15. It's -15. But I don't really care what the number is. All I care about is that this is a negative number. Because it's negative, that means my graph is decreasing at 0. And the fact that it's decreasing at 0 means that it's decreasing at all numbers from -3 to +5. I do that analysis one more time to check this third region over here. Pick any number you want that's greater than +5. I don't know, 10 maybe? 10s usually work out nicely in math. Let's try plugging 10 into the first derivative. I'd get 10 squared minus 2 times 10 minus 15. You could figure out what number this is equal to if you want, but really you don't even have to if you can just recognize that this is greater than 0. I get 100 here, and I'm not going to subtract anywhere near 100 from these two terms, so I'm going to end up with a positive number. The fact that it's positive means my graph is increasing when x equals 10, and therefore increasing for all numbers in this region here. I now have figured out the intervals on which my graph is increasing and decreasing, which will be really useful when I go to sketch the graph, which I'll do after I finish one more step. The last step is figuring out when my graph is concave up and when it's concave down. Good news, figuring that out will be almost identical to figuring out when it's increasing and decreasing. The only spots where I can switch concavity is at this inflection point right here. So if my graph is concave up at, I don't know, 0 for example, then my graph is concave up for all numbers that are less than 1. So let's test x equals 0 and see what happens. When I say test x equals 0, I don't mean plug 0 into the first derivative, but I instead mean plug 0 into the second derivative, because now I'm not interested on whether my graph is increasing or decreasing at 0. I'm interested in whether it's concave up or concave down at 0. The second derivative is 2x minus 2, so the second derivative evaluated at 0 would be 2 times 0 minus 2, which is equal to -2, which is less than 0. What that means is my graph is concave down at this point right here, but more importantly, that means my graph is concave down at all values that are less than 1, this inflection point, because my concavity can only switch signs at my inflection point. One minor thing that's bugging me, I called this an inflection point before I really even knew it was an inflection point. I knew that the second derivative equaled 0 right here, which kind of makes it a candidate for an inflection point. But it's possible that it's concave down to the left of this point, 0 at this point, and concave down to the right of this point. It's not, but it's possible that it were. And in that case, I would not want to refer to this as an inflection point, because inflection points only happen when my value changes sign, and in that case it would be negative on either side of this point. And you might think that same thing is true of critical values, and frankly, it kind of is. Okay, this is kind of opening up a can of worms, but typically the way critical values are defined is anywhere the first derivative is equal to 0, you have a critical value. So really, before, when I said critical values happen when f prime of x changes sign, that's true, that points where f prime of x changes sign are called critical points, but it's possible to have a critical point where f prime of x does not change sign. So maybe a better definition of critical points is they happen anywhere f prime of x equals 0, whether or not the first derivative changes sign at that point. And it'll turn out that it's also useful to allow points where the first derivative is undefined to be critical values. Although that's a far less common case, especially in our class. So really, we're just focusing on this first one. That's slightly different than inflection points. Just because the second derivative equals 0, it's not necessarily an inflection point the way most books define inflection points. Typically, to be an inflection point, not only does your second derivative have to be equal to 0, but also your second derivative has to be changing signs at that point, which is a slightly stronger criteria, although that subtle difference is not going to end up being important for our class. So if I've confused you in the last 2 minutes, frankly, it doesn't matter. I just want to make sure I'm not lying to you in these videos, so I want to give you the precise definitions that most books use. But for our purposes, if you want to think about critical points as when the first derivative equals 0 and inflection points when the second derivative equals 0, that's just fine. This idea of changing sign is a little bit subtle and a little bit more technical and kind of beyond what we need to do for our class. Anyways, that makes this picture work out a little bit better. My first derivative equals 0 right here. I don't necessarily know that it's changing sign at this point. I test the left, I test the right. Sure enough, it did change sign, which means it went from increasing to decreasing. And at this critical value where the first derivative equals 0, sure enough, it changed sign also. What about this point, which maybe instead of labeling as an inflection point, I should label as a point where the second derivative equals 0? Well, to the left of that point, it's concave down because we tested a value of a number less than 1, 0 in this case, and saw that a negative number came out. And if we test a value greater than 1, like, 2, for example, f double prime of 2 is 2 times 2 minus 2, which is equal to 2, which importantly is greater than 0. That means that at 2 right here, my function is concave up, and therefore at all numbers to the right of 1, my function is concave up. And really, it's only at this point where we see that not only was the second derivative equal to 0 here, but my second derivative changed signs at this point, went from concave down to concave up. Can I technically call this an inflection point? Although if you called it an inflection point, right, when you figured out that the second derivative equals 0, we're fine. It's a fine line between making things overly complicated and not lying to students that I'm trying to kind of tread lightly on. Anyways, with all this information, I think we can finally sketch the graph. And again, it's a very approximate graph. I don't care so much that this graph looks like the real graph. I just want to make sure it exhibits the proper characteristics. I want my graph to be decreasing from -3 to 5. So you're kind of picturing going down like this between these two numbers. But I don't want it to be going down linearly like this. I want it to be going down in a concave down fashion until I hit this point, and then in a concave up fashion once I hit this point. So on this interval from -3 to 1, we want to be both decreasing and concave down. So maybe my graph would look something like this. At this point where x is equal to 1, there's a very subtle change in the shape of the graph. I'm still going to be decreasing, right? I'm decreasing all the way until I get over here to 5, but I'm going to be decreasing in kind of a different way. Instead of being an upside down bowl, I want to be a right side up bowl. So maybe my graph would look something like this. If you can see this little S curve in here and understand how to come up with this graph by considering concave up, concave down, and the fact that we're decreasing, you're picking all this stuff up perfectly. I should finish up my graph, but really I want to harp on this. If you get this much, you're doing great. What's going on to the left of this point? Well, my function should be increasing, so kind of going up in this direction, and it should be concave down. So maybe my graph looks something like this. What about over here? Well, now I want to be increasing again, so going uphill, but doing so in a concave up fashion. So it's going to look something like this. Is this the exact graph? No, it's definitely not. I mean, this is just an approximation of the graph. But the important things I want you to realize is this graph is decreasing from -3 to +5 and increasing to the right of 5 and to the left of -3. And this thing is concave down to the left of +1, and it's concave up to the right of +1. And if you tried this on your own and you sketched a slightly different looking graph, but it exhibited all those features, you did it perfectly. If you're curious what this graph actually looks like, I got it graphed right here. And that's kind of similar. I mean, that's closer than I sort of expected it to be. It's not perfect, right? I mean, it looks like my x-intercept here is barely above 8 and between -5 and -6, whereas over here it's a little bit more above 8, and it's definitely not between -5 and -6. It didn't get down here until way out here at like between -7 and -8. But it basically has the right shape and the right idea, which is what I was trying to get across in this example.